In the previous tutorial, we talked about what optimization is. It's the process of finding a minimum or a maximum for a given objective function. The previous example was an unconstrained optimization example. Basically, the optimizer is allowed to move around without a limit. In this tutorial, we are going to discuss constrained optimization. We're going to impose a limit on where the optimizer can seek and search for an optimum minimum. So to start off with, you're going to need two files that are linked in the video description below. So bear with me while I play with this window here. They're model and design model PDF. So make sure you have these two files so you can follow along with this tutorial. Now let me give you some insight regarding this example. Our optimization problem statement, as always, this is a very important thing to have. The design variables will be x1 and x2. Our objective function will be the same one as before, x1 squared plus x2 squared. But now our constraints. We are going to define a new constraint expression or equation defined as x1 squared plus x2 divided by 2 all squared. And we're going to say that anything greater than 1 is an acceptable criteria. So basically, if we look at the graph here, any value for x1 and x2 outside of this green ellipsoid is an acceptable design or configuration for the objective. Now here, let's explore what Nastran or the optimizer in Nastran will do. It will start off at this initial point like before. Here, let me go ahead and show you the initial point here in red. During the optimization, it will make an attempt to go towards the minimum, but then it encounters the design constraint I just mentioned a moment ago. It understands that everything outside of this ellipsoid is acceptable. Anything inside is not acceptable, so that's why it remains outside of the ellipsoid. But then this is what it does. It realizes that once it hits the constraint, there is still opportunity to further minimize the objective function. So you see it move along the constraint towards the minimum here. Let's go ahead and replicate this example with the following tutorial. Open the web app and select the two PDF files you just downloaded from the video description. So that would be model and design model. Select these two files and click open and click upload. So this is basically our starting point from the previous example. We have our two design variables x1 and x2 and x3. We have the same objective expression written out here. But now if we go to the constraint section, we can create a synthetic constraint here. This is where we can type in that expression. And here I think I have this written down here. So let's zoom in on this. It's x1 squared plus x2 divided by 2 squared. So here let's type in that expression here. x1 squared plus x2 divided by 2.0 squared. And then the lower bound will be 1. So this is effectively creating an ellipsoid where it's saying any value outside of the green ellipsoid is an acceptable configuration for x1 and x2. Here on the right are the necessary entries for Nastran. They are created for you on the fly. Now what we can do is go to the exporter and download these two new files. And let's move the old PDF files to the side and create a new folder called to optimization working directory. I'll go ahead and go to my downloads folder and take these two new PDF files I just updated and downloaded and move them there. And now we'll start Nastran and perform this new optimization. Again, optimization is a process of finding a minimum or a maximum for a given objective function. This example is different from the one before because we have included a design constraint. The expression is g. We're saying that g has to always be greater than the 1, which is this green ellipsoid here. You'll find out in a moment that the optimizer does minimize the objective until it hits the constraint, and then it moves along the constraint until it ultimately hits a local minimum here. So let's go ahead and look at that. So we'll open this second directory and we will inspect the F06 file, and we'll go to the very bottom and make sure we have the message run terminated due to hard convergence. So that's perfect, that's what we wanted. So here we start at a value of 25. So again, this is the value at the initial point. So if I hover at the initial point here, I should expect the value for Z equal to 25. Now let's see if we can zoom in and see what the value is at the minimum. The minimum, which is indicated by this yellow X, the minimum is 1.01 for Z, and the minimum is located at 1, 0.05. Let's look at the F06 file and see what we have. The Z, or objective value, is 1.01, just like the graph. And here, the final X1 and X2, we see that it's 1 and 0.06. So of course, we will have a slight difference in the values, but it's close enough where we can say we have reached the objective as expected. Like before, you can go ahead and take the Excel template and produce plots of your own. So let's go ahead and do that. Let's go ahead and copy this and move it to the directory. This template is also linked in the video description below and will help you make these plots. So here we have a plot for the objective. We start at a value of 25, and maybe I'll go ahead and add a data label here. And then at the very end, we end at a value of 1.01. So let me go ahead and add that value here. And then again, we started off at the initial point of 3, 4, and we ended at a value of 0.06 and 1. And these are the same values that we have on the graph. So again, I like to reinforce the fact that optimization is the process of finding a minimum or a maximum for a given objective function, in this case f. This one is different from the previous example because we've included a constraint. Once you start performing formal structural optimization, your constraints might be stress constraints or displacement constraints. So if you can understand this example, once you switch over to structural optimization, the concepts will be the same. In the next tutorial, let me go ahead and see if I can open that now. We are going to cover what's called side constraints. These are basically constraints on the design variables themselves. An example of this might be the cross-sectional area for a structural member. You want to impose a side constraint saying never be less than 0. There's no such thing as a negative area, so you want to make sure there is a lower bound. And maybe you might have an upper bound of, say, 100. These bounds on the design variables are known as side constraints. And in the next tutorial, I'm going to guide you on how to set this up, and we're going to explore what the behavior is with the same familiar graphical example. Thank you for watching.